So we all know Python as the language for data science, machine learning, and artificial intelligence. However, Python is also an optimal tool to solve optimization problems. Today, in the next 20 minutes, we will try to understand which tools Python can provide us with to solve mathematical optimization problems and how serverless infrastructure can help us making our solutions more efficient and by staying cost effective. But before doing that, we need to set the stage for a very complex and important problem. We will go back in the past, far in the space. Let's go to California in 2018. In 2018, California was the first state of the United States to commit to 100% renewable generation by 2045. It was a bold move from the Democratic governor of the state, one in stark contrast with the US President, Donald J. Trump. Still, California, up until 2018, was a shining example in energy transition. From 2009 to 2018, it has raised its share of renewable generation from less than 4% to about 25%, mainly thanks to the rise in wind and solar production. However, when in 2018 the new energy policy was announced, not everyone was smiling. And I'm not referring just to Trump supporters, I'm also talking about brilliant and rational engineers at CAISO. CAISO is the California Independent Transmission System Operator, the organization in charge of managing the high voltage transmission line in the Golden State. Think Terna in Italy, it's exactly the same thing. Since 2012, CAISO was warning about the so-called duck curve. In the future, they were saying solar generation will be so predominant that in the middle of the day we will have too much generation, and in the evening we will have too much demand and not enough generation to meet it. You see this curve? It goes worse and worse from 2012 to 2020. This chart is from a report published in 2013, so 5 years before the energy policies that I'm talking about, and it has forecasts up to 2020. So there is a real problem here, and you would think that this problem being known since 5 years before, they would have done something to solve it. No, they didn't. They didn't, and the consequences are here. In 2019, 4% of the total solar generation in California was curtailed. That means wasted. That's enough energy to power a city like Florence for a whole year. This energy was clean energy, zero-cost energy, wasted because there was not enough transmission lines to transfer it to other states in the US. So within the same country. Good. This issue brings us to our problem. We need to model power systems and power markets, but we need to model future power systems and power markets, because we need to take now strategic decisions that will result in good or bad consequences in years, if not decades. So when we have to face problems like this, engineers have to make models. For one of our customers, we created a system that is capable to create scenarios for the European power market up to 50 years in the future. In doing that, we faced an interesting problem. That is, how we solve the duck curve. Well, the solution is already known. We need some kind of storage to drain power from the grid during daylight, daytime, and release power into the network during nighttime. This technology nowadays is lithium-ion batteries. It can be a different technology in the future. The point is that we are not sure how these plants will work into the power systems. This is an idea of how utility-scale battery packs will look like, and that's a rendering from General Electric, because there are a handful of plants like that in the whole world. There are a couple in Australia, 3 or 4 in the United States. There is some experimental plant in Europe, but that's basically it. So we need to model something that does not really exist yet. How can we do that? The answer is, let's resort to mathematical optimization. We can assume that the actor in charge of operating the battery packs will try to maximize its economic profit by complying with the technical limitations of the batteries themselves, because you don't want to burn down something that is worth tens of millions of dollars, of course. Now, welcome to Mathematical Optimization 101. I will try to squeeze a very complex topic in 2 minutes, and bear with me. In mathematical optimization, we have two great families of problems. We have convex problems and we have non-convex problems. So I'll get in a minute to explain what a convex problem is, but the point is that as long as we stay in the convex problem family, we have a complete mathematical discussion about that. We know how they work, we know how to solve them, we have very effective and efficient algorithms to solve optimization problems with thousands of, even tens of thousands of variables. If we go into non-convex problems, we are in troubles. They're very hard to solve, and as of now, we have no general purpose algorithm that can give us guarantees about the solution. We know how to solve efficiently a couple of families of non-convex problems, but they're very niche cases, like computing the PCA of a matrix. We know that the solution is the eigenvectors of the matrix, but we do not have a general algorithms. So now, when is a problem convex? From now on, I will talk just about minimization problems, because a maximization problem can be framed into minimization 1. If you want to get the minimum point, if you want to get the maximum point of f of x, you can just look for the minimum point of minus f of x. So we will talk only about minimization. A problem is convex if you are minimizing a convex function on a convex feasible set. So you have to show that the function is convex and the set of the feasible set is convex as well. For the set, it's usually easy, because if you limit yourself to linear inequalities and to greater than or smaller than constraints, then you're guaranteed that the feasible set is convex. The difficult part is the function. A function is convex if first, a set is convex if you can join any 2 points with a line without going out of the set itself. That's the definition of convexity for a set. A function is convex if the area of the space where it is defined over the surface defined by the function is a convex set. In other words, you should take any 2 points on the surface described by the function, and you should be able to join them with a straight line without going below the surface defined by the function. Okay? Okay. Which of these 2 functions is convex, right or left? Good. That was easy. However, how many optimization variables do we have in our problem about batteries? So again, we want to optimize the economic profit of the actor operating the batteries, respecting the technical limitation of the devices for 50 years in the future for tens of different types of batteries. So even without taking into account the different types of batteries, we have like 400,000 optimization variables. Multiply that by 50 kind of batteries, you go into the 20 million kind of variables. Good luck trying to chart a function like that. It's impossible. I mean, we cannot draw anything above 3 dimensions. We are going to 20 millions. So no. How can you check if a 20 million dimensional function is convex? The good answer is you can't. You can try with sampling and checking the definition, but that's a huge space. You're never going to cover it in even a small portion. You can try and show that it is convex by hand. Good luck again. However, the guys at Stanford came up with this very interesting idea of disciplined convex programming. That is, you should not check if a function is convex, you should build the function so that you know that it is convex. We have some mathematical rules to build function and preserve convexity. For example, the easiest one is that we know that if we sum two convex functions, we are going to get another convex function. There are many such rules. Some of them are as easy as the one I just presented you. Some are more complex, but they can be automated. So if you draw your function from a specific set, and if you follow just basic operations such that sum, multiplication, division, subtraction, function composition, which is basically everything you want to do, then you can check immediately if a function is convex or not. How can we do that in Python? Well, we can use a package called CVX Pi. CVX Pi is great. I mean, it simplifies a lot the way you define convex optimization problems. It gives you a set of functions that you can use, and it gives you a lot of operations that you can perform with such functions. Here is an example from their documentation. The idea is that you have a matrix A, a vector of optimization variables x, and a vector of constant parameters b. And then you use the sum of square function, which you are guaranteed giving a convex result. Because squares are convex. If you sum a number of convex functions, you preserve convexity. So you know that the objective function at line 10 is convex, no matter what is in A matrix and in the B vector. It doesn't matter. It's convex. Great. So now we know how to build our optimization problem. If we solve it, oh, by the way, another great stuff that CVX Pi does is it translates this formulation into matrices that then get passed to the low-level solver. So you don't have to build the matrices yourself. You just define the function with the disciplined convex programming paradigm, and then you let CVX Pi do the job. That's great. Very good. We now know how to define our problem. Imagine that here the problem is not something like a constrained linear regression, but it's something like a, let's say, a maximization of economic profit subject to technical limitation of batteries. The solution is something like this. The colors are different kind of batteries. This is 24 hours within the day. And you see that the battery is releasing energy, so it has a positive exchange with the network during nighttime and during evening, and it's drawing energy from the network, so it's charging itself during daylight, because it's basically flattening the dark curve and taking the excess energy produced by photovoltaic plants. That's great. But here comes our iguana, and the point is, okay, good. You know theoretically how to write and to solve the problem. Now the point is, have fun doing that. Still, you have 20 million variables, and even if it's a convex problem, it's still 20 million variables. Imagine just creating a 20 million by 20 million matrix of floating point values. Tough luck. The first time I tried, NumPy told me, Lele, you're trying to allocate memory for 2 terabytes. Do you really believe you can do that? No, you can't. Of course you can't. You must be smart. And the way of being smart here is using sparse matrices. So the matrices in our optimization problem are mainly made of zeros. And zeros can just be neglected. We can just save the information about where the non-zero elements are and what is their value. This saves us a lot of memory. And this makes also the solution of the problem much more efficient. Is it enough? No, absolutely no. We must be smarter. The point is, you have to solve the problem for the next 50 years, but is every day dependent on the previous one? Theoretically, yes, because you preserve the state of charge, but these type of storages are meant to work in a daily cycle. So they charge during daylight, they discharge during the night. They're not meant to preserve energy long time. Also because lithium-ion batteries do not work in the long run. You need other type of technologies that we do not have right now. We can use, pumped hydro in the Alps, but it's difficult. So we can divide and conquer. We can say, why should we optimize for 50 years? We can optimize for every month, or for every week, or for every day. Empirically, we understood that the best way to do it is to optimize for each month. So you don't have a huge optimization problem. You have 50 times 12, so 600 smaller optimization problems. Then you have, of course, to force boundary conditions to preserve the energy conservation principle. You can say that the batteries are halfway empty at the beginning of the month and halfway empty at the end of the month. It's reasonable, it's a simplification, sure, but it's not very different from how the real world would look like. Great. Now we have 600 small optimization problems that we can solve independently from one another. Why shouldn't we run everything in parallel? Because we don't have 600 cores on a machine. But we can spawn 600 Lambda function. Why not? They can run in parallel. And here is where the serverless computing comes into play. What we do is to have a cloud composer, which is basically the Airflow that you pay a lot on a Google Cloud Platform, orchestrating a pipeline. At some point of the pipeline, it writes some input data on a bucket. When each file is written on the bucket, a cloud function is spawned. So we have 600 files, 600 cloud function, one for each optimization problem. And each function solves an instance of the optimization problem for a single month. Then it writes the results again in another bucket. The orchestrator is pulling the bucket. When it has 600 files, it merges all the results, and it goes forward. How long does it take? Well, 5 minutes. With the serverless solution, we basically skewed the time that it takes to run the whole optimization on 50 years to the time that it takes to run the optimization on a single month. Because GCP will give us the infrastructure and the elasticity to scale up to 600 parallel executions. So the question is really, how long does it take to solve one optimization problem and to start, and for the cold start of the cloud function to kick in? It's 5 minutes. Good. And that's it. That's how you solve complex mathematical optimization problems with the help of CVX Pi, some mathematical knowledge that you have to get, and serverless computing. I am Emanuele Fabbiani. I'm head of AI at Extreme, where we solve business problems with artificial intelligence.
Some questions will start appearing on the slide. The first one is, why serverless? Any consideration on cost vs using spot instances?
Any considerations of it?
Spot instances.
Oh, spot instances. Just because it was easier to code this stuff on cloud functions. I mean, the idea is to have a lot of computing power for a very short amount of time. And cloud functions are great because they spawn very quickly and they cost very little. I mean, a full run of the full optimization problem on 50 years, it costs like €3. So very affordable.
That was the only on Slido. There's someone else in the room directly that want to, yeah.
like mathematically, what's the kind of optimization problem when you write down all the constraints? What type of optimization problems was it that you applied in this specific case?
So the real problem would be non-convex. So we designed a convex relaxation which translates ultimately into a quadratic optimization problem. Constraint quadratic. Yeah.
We have another question on slide 2 before. How much did it cost to run 600 function?
3 years.
3? Oh,
3 years, yeah.
there's already an answer.
Outside the free tire, that is.
Yeah, great talk. Can you elaborate a bit more on orchestrator in case of the Google Cloud? Is it like you configure it on the UI, or is it the code that you can reuse for another optimization problems?
Oh, cool. So you asked the orchestrator, right? Yeah. Okay. The orchestrator here is Cloud Composer, which is a hosted version of Airflow. So it's basically Apache Airflow, and we wrote all the code for the scenario generation as Airflow tasks. So Airflow is managing everything, and then when it needs to call the functions, it goes to write files in a bucket. So the cloud function is basically just a main. Of course, it's the function with the usual GCP format, but it's like a main where we use the modules that could be used everywhere else. So the module that solves the optimization is completely abstract. Then it's just, let's say, used inside the script in the cloud function. So it's completely reusable.
Thank you for the presentation. My question is more related to the low level of the processing.
Mm-hmm.
I'm involved in very heavy computational processing. And in the past, before the cloud era, I'm thinking about 10 years ago, we decided to develop most of the stuff in C code, okay? Mm-hmm. For what you have seen in this specific case, Python code is now ready compared to Rust or C code or matter application to do very heavy computational in reasonable time and reasonable cost, or the solution to move to C code and Rust is still a good solution, or a good strategy?
Okay, great question. The answer is no, it's not. The computation is performed in C. The idea is that CVX Pi uses low-level primitives that are written in C. So the idea is that you use Python as a, sorry, maybe he has, okay. You use Python as a developer-friendly interface, but then the heavy lifting is performed in C.
Yeah, exactly what we did. So thank you for this. And just because we talk a lot about Rust during this conference, and I was very surprised, and even it's a pleasure because I'm very interested in. What is your opinion in the comparison C and Rust? If you have the way to do so,
Okay, so for this specific use case, I'm not sure if Rust will ever catch up with C code. Why? Because we know how to solve efficiently convex optimization problems we have been knowing it for many years now. And we already have some very good C libraries in C made by very good researchers, and it would take a lot of effort from very specific people to rewrite everything in Rust. And I'm not even talking about the risk of messing up with bugs and so on. So I don't see how this will happen. What I see is that from a certain point on, which I'm not sure how far it is, people will start using Rust to write high-performance code. So the idea is that the newest packages will be probably written in Rust, but there is so much legacy code here that there is no way they are going to rewrite everything. It's not economically feasible.
We have another question on slide 2. That is, how sparse was the matrix?
I mean, very, very, very sparse. So it's like 99.9990. It's mainly the main diagonal and few other spots because the matrices were built from let's say, they were built from automatic translation of functions like this, and they were just made to compose other pieces. So the big square matrices were almost completely sparse. So the gain in memory footprint was huge.
We still have 5 minutes if you want to ask other questions. Okay, we have other two, one moment. So, did you consider other approaches to decompose the large problem? For example, with ADMM?
No. ADMM is great. I've used it during my PhD. But if you don't have to use it, maybe it's better not to use it. Because, I mean, if you can frame everything as a quadratic problem, why should you go for ADMM or other advanced topics? I mean, it's the simplest solution and it does the job. So I would say that it could have been possible to use ADMM, but it was not probably the simplest solution. So we opted for this one.
Right. The other one is, any considerations using an OSS solver like CVX Pi over commercial software like Gurobi? Are you using majorly OSS solvers in productions?
Let's say they're not the same thing. So CVX Pi can be used with Gurobi for the low-level optimization. So CVX Pi can allow you to write the problem in discipline Convex Programming and then translate everything into matrices that then get pushed down to Gurobi or your favorite solver. What we did was to take the best, let's say, 5 open source solvers and benchmark them. I can't remember which one we chose, but it's completely free. It's open source. Maybe I will add it at the end of the slides. And we didn't even try Gurobi because, I mean, why should we pay for commercial software when the gain is basically non-existent, because 5 minutes are already more than enough for our use case. I must say that I did use Gurobi for my PhD when I had to solve a pretty annoying non-convex optimization problem with, let's say, alternate coordinate descent. And there, Gurobi was superior to anything open source I could find. But it was a very specific use case. I mean, if you stay into the realm of quadratic programming, I mean, the algorithms are well known, so you don't have to go for something commercial that may be better, but just marginally better.
We have room for maybe 1 or 2 questions. Someone? No, okay. Thank you very much.
Thank you.